Hi, everybody. I was asked by a couple of students via email to go over the process for mole conversions in stoichiometry. This video that I'm doing right now is going to talk about the process, and then when I'm done with this one, I'm going to make another one where I work a couple of examples. So if you're looking for examples, go look at the other one. If you want a review of the process, this is the video for you. The basic process that we're going to use for mole conversions and stoichiometry is known as dimensional analysis, and you've probably seen this in the past as some type of unit conversion, such as convert 5.5 feet to inches. This is the basic equation that we would use to set that up. This first number, the first fraction, is built by taking whatever quantity we are given with its units and then simply placing that over 1. So everything that we're looking at so far just simply comes from what we were given, right? This 5.5 feet gets placed here, and then the 1 goes in the bottom just to make it look like a fraction. Now the second fraction is what we call a conversion factor. So in the rest of this presentation, when I talk about conversion factors, I'm meaning the second deal in the second fraction, and we're going to build the second fraction by putting 2 equivalent quantities into the top and the bottom of this fraction. So the idea here is that 12 inches and 1 foot are 2 different ways of expressing the same length. The way we decide what goes in the top and what goes in the bottom is so that we can get units to cancel out. So we put 1 foot in the bottom so that it cancels out the units that we were given. So whatever you're given is that the part that matches that has to go in the bottom of this conversion factor. The top is going to have the same units as the thing that you're trying to find. In this slide, I just tried to write out what I said on the previous slide as I went through setting up that conversion. The heart of both mole conversions and reaction stoichiometry is the concept that the 4 things on this graphic are all equivalent to one another. Start in the middle here with this 1 mole. 1 mole is defined as 6.02 times 10 to the 23rd representative particles. Now remember, representative particles are things like atoms, molecules, and formula units. That means the smallest piece of a substance that still is that substance. So if you just keep breaking it into smaller and smaller chunks, you eventually get down to its representative particle. Then if the substance that we're talking about is a gas and you have 1 mole of a gas, it'll occupy a volume of 22.4 liters at conditions called STP, standard temperature and pressure. These conditions are very close, but not exactly room temperature and normal pressure. Then the 4th thing that these things are equivalent to, or that 1 mole is equivalent to, is the molar mass of the substance in grams. So molar mass is that thing we calculate by going to the periodic table, looking up the mass of each element, and then multiplying that mass times the subscript on that element in the formula for the compound. So all 4 of these things are equivalent to one another, and we can use that as the basis for our mole conversions. If we look at a balanced chemical equation, what exactly does this mean in terms of these numbers, right? There's a 3 out there in front of the hydrogen and a 2 out in front of ammonia. And even though it wasn't written, there is a 1 out there in front of the nitrogen. So what do those numbers actually mean? Well, we're going to interpret those numbers as moles. So what this equation, this balanced chemical equation, is actually telling us is that 1 mole of nitrogen reacts with 3 moles of hydrogen, and they will produce 2 moles of ammonia. Well, we're going to use this as the basis of equivalence for our dimensional analysis problem for reaction stoichiometry. I'm going to do just a little tricky math thing here. to make this look a little different without changing the value of anything. There we go. What I did to get this bottom line is I factored out the coefficient from the expression right above it. And the reason I did that was to get something that looks like the radiation sign. The center of that radiation sign says 1 mole. So now the thing in parentheses on each of these expressions is 1 mole, something straight off the radiation sign. Well, the 4 things on the radiation sign are all equivalent to each other, which means I can substitute any of those other 3 quantities for the 1 mole. For instance, I can replace the 1 mole of nitrogen with the molar mass of nitrogen. If you go to the periodic table, each nitrogen atom is about 14, and so if we double that for N2, we get 28. In addition to that, I could substitute the volume of 1 mole of gas at STP, which is 22.4 liters, or I could substitute in Avogadro's number, 6.02 times 10 to the 23rd molecules of each of these substances. So notice that in these expressions, I've got the coefficient out front multiplied by something off the radiation sign, whether it's 1 mole, the molar mass, 22.4 liters, or Avogadro's number. That's the radiation sign is whatever the second thing here is. But here's the thing that's so cool about all of this. All of these expressions, all 12 of these expressions, are equivalent to one another. So to do our reaction stoichiometry problems, to convert, say, grams of nitrogen to grams of ammonia, we can pull whichever 2 of these conversion factors we need. And they all follow the simple format of the coefficient times a number off the radiation sign. All right, so when you are getting ready to take the test tomorrow, or when you're looking at one of these problems on the test, you can recognize, oh, this is going to be one of those dimensional analysis problems, but which approach do you need to take? Is this going to be a mole conversion problem, or is this a stoichiometry problem? So the question you need to focus on is how many chemicals are mentioned in this particular problem. So let's say the question says something like, how many molecules of methane are found in a sample of 100 liters of methane? Well, we've got liters, we've got molecules, but we only have one chemical. It's methane all the way through that problem. So if there's only one chemical mentioned, when you build those conversion factors, we're only going to put one number. And that one number is going to be something off the radiation sign. But let's say instead it's something like you have 25 grams of nitrogen that react according to this equation to produce ammonia. How many liters of ammonia can you produce? Well, in this example, we had 2 chemicals. It's talking about nitrogen, and it gave you a number for nitrogen, but then it asked you to find a number for ammonia. With 2 chemicals, we need to put in 2 numbers. The first number we're going to write comes from the radiation sign, and the second number we're going to write will be the coefficient from the balanced equation. If you want to see some worked examples, please take a look at the other video that I'm posting along with this one.